we talked about data distributions. We talked about descriptive statistics, where you're basically you use that to describe your data, to understand the shape of your data, if it's parametric or non-parametric, if there are things like correlations or distributions, like in the variability or variation of the data that make patterns. But you're not inferring anything. And inferential statistics is when you're asking a question of your data. So you kind of want to know if your data from this treatment or from this day is different from your data on that day or that treatment. And so we're going to go back over data distributions kind of quickly. This is where I left off, believe it or not. So in order to know how to make your data meet the assumptions of normality and become sort of parametric, which is what you need for inferential statistics, you need to understand your data distribution. So this is sort of going back to the descriptive statistics I discussed last week. But what we're looking at here are the different shapes, the different ways your data can be distributed. And so you guys, I've noticed that you guys have like a cool pointer that you can use. How do I do that? Oh, there, pointer options. I'm going to give it a try. Laser pointer. Oh, nice. Okay. Now, back with you. So we're all familiar with this sort of symmetric, unimodal, normal type distribution. And we know that from even any basic statistics class you've ever had, that this is what you're going for. But in reality, your data might look much different. You can have uniform data. You can have left and right skewed data. You can have bimodal or multimodal, it's hard to say, try that, multimodal data. And then within that, there's even more specific mathematical distributions or descriptions that you could use to describe this. So uniform data could also be Bernoulli data, which is sort of when you have a yes-no on-off style distribution, which is 2 points. You have binomial distributions and Poisson distributions, which appear to be a little bit skewed. And then on a serious change of that, you can have geometric and exponential distributions. Within those, there are these other shapes like gamma and beta distributions, which look very similar to chi-square and Weibull. And then we've got our classic normal or Gaussian distribution, which could also turn into a log normal or student tease distribution. So there's a lot going on when you look at your data, and it's always good to inspect your data. Now, the question is, how do you do that? Well, what you're really looking at is the types of measurements you've made should be sort of categorized on the x-axis, and then the number of, and they're almost like bins, and then the number of data you have that falls into that measurement category or range is a bar. So you have to think about your bin size. When you're making a histogram to see what your data looks like, the smaller your bin size, the more fine of a scale you're going to have in terms of looking at the distribution. If you make your bin size really big, you're going to have a very blocky looking distribution. It's going to look, like Minecraft pixelation versus, I don't even know what you want to call that, icicles. Beautiful Christmassy themes here, winter themes, I mean. So it's always important to consider your bin size, and basically you should think of the range of your measurements and make sure that you have a bin size that is going to give you a better view, because this is actually all the same data. And I'd say that the bin size of 1 and bin size of 0.2 are giving you very similar looks or, distributions. Although here you're seeing 3 sort of modes, here you're seeing 2. And if you pick a bin size of 5, you're only going to see 1 mode, 1 mean. And that's why it's important to decide how fine a scale it's going to be. There's no rule of thumb, but obviously you can get the bin size down to such a small degree that it doesn't look like you have a distribution at all. It could just look like a bunch of noise. So bin size matters. And so it's nice to pick something sort of in the middle. All right. What is a data transformation? So if your data is shaped in a way that prevents you from performing a test that's inferential, and you really need that inferential test, then you can transform your data or try to transform your data into a new shape that allows you to conduct that type of test. So usually this happens when you have non-normal or non-parametric data and you really want to do a parametric test. So you can think of it as a function. The most common ways to transform your data are the log x function, the inverse function, which is 1 over x, or a reflection, which is 1 minus x. And this can give you a different, you can see how even combinations of these might take you from a beta or chi-square style distribution to something that is shaped something more like a normal Gaussian or t-test distribution. So when do you want to do this? Like I said, when it doesn't meet the assumptions for a statistical test. And also, sometimes you do this for scaling purposes. So you might be familiar with this. In proteomics, we do what's called Pareto scale all the time with our data, because the scale of the mass spectrometer is so large that we tend to have a lot of zeros when we have non-detects or blanks even. And then we also have data that just follows a really big range, like sometimes in the up to 8 or 9 zeros after your first one. And that makes things a really big scale. However, if you want to do a PCA and you want to have your protein data paired with water quality data, you have to scale so that they're at the same scale. I mentioned this last week. And so sometimes you do a data transformation, not because of assumptions, but to make sure that your data is scaled appropriately for certain tests, like modeling and PCA. So here's an example. And I call it a relevant example because I was really excited to find this distribution. It was just the number of fish and the percentage. I don't know how I found this online. I was like looking for examples of distributions of things. This would be a log normal distribution. If you take, and this is a log normal, but it hasn't been logged, right? So if you have a distribution that looks log normal, which goes back to that first slide I started with, and perform a logarithmic transformation, the number of fish suddenly appears. I mean, it's going to get much smaller because we're bringing down the number of zeros. That's always what happens. But now you've got something that looks a lot more like a parametric style distribution that would hopefully allow you to meet most of the assumptions of normality and get you to the parametric test you may want to perform. Okay. This also brings us to another concept, which is called the central limit theorem. So if you're thinking specifically about normal distributions, there is this theorem, although I think about it, I'm like, I'm not sure if this is always going to be true, but it's out there. So let's talk about it. If the sample size is large enough, your data will always follow a normal distribution, no matter what the original population distribution is. This is what they say. This is what this theorem says. So for instance, let's say your population distribution is, I forget what this is called. Was this unimodal or something? It wasn't even unimodal. It was, I don't know why I can't remember. But if you have this like constant, sorry?
Uniform?
Thank you, uniform, awesome. So if you have this uniform distribution or something that looks more bimodal or sort of skewed or chi-square-ish, this shows you that if you sample, so this is just math, if you sample with an N of 5 across any of these distributions, what's going to end up happening if you've done it randomly, you're going to likely get a distribution that looks something like this. If your N increases to 30, the actual distributions start to look the same. I'm not sure how this is possible because I've never actually done it, but someone's done the math and says this is actually how this works. So basically the central limit theorem, and it's a mathematical condition, is that if your N is greater than or equal to 30, you will have a normal sampling distribution. But like I said, this really isn't intuitive to me. I don't actually somehow, like when I think about this, I'm like, no, this can't be true. But someone's worked this out. So the point I'm trying to make here is that of course, the larger your N, the more likely you're going to get a distribution that's going to meet the assumptions that you may need for good, robust statistical testing, and that you probably never need an n greater than 30. All right. The data distributions, and so these are issues and with this data distribution and transformations you can try to take. These are general sort of rule of thumb sort of things that I pulled out of a really awesome online statistics thing that I found. So, okay, kurtosis. There's different types of kurtosis. So let's just talk about that. There's mesokurtic, which is when you have your regular symmetrical normal distribution. There's leptokurtic, where the distribution has a high central peak and sharp asymptotic tails. I have to say we see this a lot in our proteomics data after we transform and scale it. It tends to look like a leptokurtic. I mean, anyone who's already looked at our data will know what I'm talking about. It's just like a really sharp peak. And then when we do something like a log or a cube transformation, we tend to get something that looks more platykurtic. So it's symmetrical, but it gets kind of flattened in the center. And so we're always, I find in our data sets, we're always sort of striking a balance between these three things. And the goal is to get to the meso, but a little bit of platykurtosis or leptokurtosis is not the end of the world. So there's no agreed upon approach for transforming your data for this. Most people proceed with parametric tests, even if it's a little platykurtic or leptokurtic. Some people suggest identifying outliers and removing them, because an outlier over here and over here, for instance, may make your data more platykurtic, or a few outliers up in the middle of your distribution, which shouldn't be an outlier, might help reduce your leptokurtosis. But I don't think that, I don't buy it. Okay. If your data distribution is skewed, so this is when your distribution is lopsided or asymptotic as well, asymptotic as well as asymmetric. So there's lots of different distributions that look like this. You've got your Poisson, Pareto, chi-squared, normal distributions. Most people suggest, well, it's just sort of where you are. You could try a square root transformation. You can try a logarithmic transformation or an inverse transformation. So it just depends on how far to the skew and how asymptotic basically your data is. And if it's on the left side, you do regular transformation. If it's skewed towards the right, you can try reflection plus that same transformation. So here's a reflectant square root, reflectant logarithm, and reflectant inverse. So this actually works pretty well. I mean, the example I showed you with number of fish that I called relevant, it worked perfectly like this. We had a log distribution, and when you transformed it with the logarithmic transformation, it looked pretty good. So this is pretty common in our data. We've been doing this a lot. So we do a Pareto scale. Our Pareto data often looks like this. So when we Pareto scale it and then do a logarithmic or a cube root transformation, we tend to get something that looks pretty good. Data distribution issues and other things to know about. So the worst one is the bimodal. I think the bimodal, multimodal data really is the hardest. And when you look at it, it just sort of like makes you feel like, I don't know what to do with this. But in fact, one of the things you can do is a pretty simple, what's called a Box-Cox power transformation. And this is what it looks like. I think that my animation here was off. I didn't expect this to show up first. But anyhow, the Box-Cox transformation is kind of like a reflection paired with an inverse and a log. So it does have a similar effect to a log transformation. And some people suggest that you try a log or an inverse transform before you try the Box-Cox. But the Box-Cox should get you to something that looks more normal. Thinking of you, Chase, since you're there, since we just saw that you had this weird bimodal data for your, was it blood glucose control group? I mean, I wonder, I think that's what it was. I wonder if a Box-Cox might help there. Just curious. Not that we need to, but maybe it's just be kind of fun to test, I guess. Because, and for anyone who doesn't know the details, Chase just did a non-parametric test and we still found significant differences. So, I mean, that's probably just as good. That's what you can do when you have non-parametric data. You can do non-parametric tests. So all of these transformations aren't always necessary if you know what to do with non-parametric data, which I'll talk about in another moment. So the last type of issue with data, I think, that I'm going to talk about is called heteroscedasticity. It's really hard to say. Heteroscedasticity. There we go. This is when the variance of the data differs between groups. So you sort of can have non-biased homoscedasticity. You can have biased, which is sort of when you see like a correlation or a regression style distribution. And you can have bias that sort of goes up and down, but is really hard to sort of sort out. The average is still a line, a straight line. When it's heteroscedastic, it means, so you can see that the variation at the beginning and at the end is about the same all along. But heteroscedastic data starts out with a smaller distribution and then gets bigger. So this is sort of, as a quick concept that I can share with you guys that most of you should know, this is that concept that when you get to the end of a larger measurement, say perhaps with a pipette, your error tends to get bigger. So at 5% error on a pipette at the low end sometimes turns into a 20% error on the high end. And it tends, in my experience, this tends to be the sort of bias that can occur in data that you've sampled using some sort of instrument that sort of got pushed to its limits of range of linearity. Once you get outside of the range of linearity with chromatography or mass spectrometry or photospectrometry or a pipette, you are now sort of entering the territory where you may have heteroscedastic data. The way to look at this is when you do inspect your data and you do what's called a residuals plot. And you can also conduct a Bartlett's test to figure out if your data is heteroscedastic or homoscedastic. I have a problem. Okay, so the sample means must come from populations with equal variances for ANOVAs and linear regressions. So you want your data to look like this for doing those parametric ANOVAs and for linear regressions. And if it looks like this, then you should probably try to do some sort of transformation. They usually say you can fix this with a square root or a log transformation or even an inverse square root. So you'll find that you're using the same transformations every time. And I could see how an inverse square root would actually probably solve this average unbiased or the biased heteroscedastic pretty well. I think if you had something like this, yeah, I don't know if that would work as well. All right, are there any questions about these transformations? I do feel like today's lecture is going much better.
I have a quick question, sorry.
Yeah.
Do you normally choose one and test it and then see how normal the distribution is, I guess, like if it passes the test and then like go ahead with it, or do you like try all of them and then make a decision, or how do you usually go about that?
Well, when we're looking at our data on MetaboAnalyst, for instance, it's pretty easy to try a few different transformations and inspect your data to see if it looks normal. I think this works pretty well on our other software called MPP. So this is specific to proteomics data, and probably as well for metabolomics data. But if you're not talking about that kind of data, we're just talking about in general, I would start by doing the test to find out if your data is normal, heteroscedastic, skewed, and there's tests for each of these, right? And they're usually standard in your stats packages. And if you use R, then there's certainly a lot of options for scripts. I'm sure like you can find, it's probably like 101 for R. It's like, here's how you do your tests for assumption of normality. And so I would start that way if you can't just plot your histogram. But you should also plot a histogram. So most people say you start with a histogram and look at the distribution of your data and you conduct those tests. If you don't meet the assumptions of normality, the histogram should give you a good idea of what the problem is. Like, is it bimodal or is it skewed? And then, yeah, just try one by one these transformations, but starting with, if it's, I think I said for skewed data, it's pretty straightforward, right? So if it looks like a log distribution, try your log transformation. You have some sort of experience with that, and you get a little bit more comfortable. When you see something that's off, you'll know exactly which transformation to apply, and then just replot it. And your software should do that for you, so you can look at the new distribution of the transformed data. And then if it meets most of the assumptions and you conduct those tests again, then you can move forward with the parametric inferential statistics. But if you can't get there and you're starting to get frustrated, why not consider a non-parametric test? There are a lot, and they usually work just as well. So I'm going to talk about that right now. Did that answer your question?
Yeah, thanks. That's great.
So the process of using data analysis to deduce properties of underlying probability distributions. So that's a long way of saying actually asking the question of whether your data distribution has changed due to something like time or treatment or some other controlled variable in your experimental design. This usually is inferring the properties of a population and then doing testing. And so then you derive estimates. So because you kind of assume for each of these tests in inferential statistics, you assume that the population distribution has a certain type of distribution, usually normal for parametric, but doesn't have to be. You can do non-parametric and be okay. That allows you to then conduct tests. Always assuming that your data is sampled from a larger population. And this is basically that comparative statistical approach, like I said, where you want to compare groups. So the easiest form of that is when you're comparing two groups. And there's a couple of different tests for this. The first one's called the one sample t test. What the hell is going on? I'm getting like a million beeps. I don't know if you guys can hear my phone beeping. It was happening earlier too. I had like 20 all in a row. I feel like it might be a service issue. Okay, sorry. I got sidetracked. So the sample test, one sample test is when you're actually testing the distribution of your data against a sort of general theoretical distribution. You can do a two sample t-test, which is when you're comparing one group to another group, which is what most of us tend to do. And that's most common in toxicology. So we'll have our control group and our treatment group, and we'll do a t-test to see if the number of tattoos are different. If you're doing a one sample test, then you're sort of asking, is my mean different from the theoretical mean, or the mean that I've read online as being the one I should have? And that's your null hypothesis. Basically, you're just testing to see if anything's changed from the null. You can extend this for count data for possibly non-parametric data that's count data by doing the Fisher's exact test. So just to go back quickly, this is a test that assumes normality and is considered a parametric test, but a similar non-parametric test you can conduct is called the Fisher's exact test. It's considered a 2x2 contingency table test. And so what you're doing is trying to figure out if your number of observations in each group is sort of different, the ones that you've observed, from what would be the expected distribution if everything was, normal. So the assumptions are that you have random sampling, independence, mutually exclusive groups, and you use this test when you want to find out the difference between two variables, and that variable is either categorical or proportional, and you only have two options. So you're sort of looking at that binomial data that I described last week. You definitely want to have independent samples. So if you're sampling the same thing over and over time, that's not independent. And you have to have less than 10 in a cell. So I guess what that means is in one group of count data, you wouldn't want to have an N of greater than 10. At that point, you want to use a different test. So this is meant for a smaller sample size. So when you need to do these two sample tests and compare two groups, how do you know which one to do? Well, first of all, you can look at your data. Is it parametric or non-parametric? If you're not sure, here's some rules of thumb. So if you have parametric data, you can do the student t-test. So if it looks parametric, if it looks normal, then you can do the t-test. But if you have non-parametric data, perhaps something that's really bimodal and you're not sure what to do, you can also do a Mann-Whitney. And in fact, this example isn't bimodal. This is two skewed data sets, which have a non-normal distribution. You can do a Mann-Whitney U-test. So this is the equivalent to this test. So here you're looking at sort of the mathematical test involves this equation of a curve. Here you're doing a mathematical test that has to do with the number of bins and the modes changing, versus here would be the means changing. Another kind of cool concept is the paired t-test, and then its equivalent as a non-parametric test, which is called the Wilcoxon signed rank. This is when you sample your data repeatedly, so before and after, as a good example. So this is when your measurement is on the same subject, but at 2 times, resulting in a paired set of observation. And you use this to determine whether the mean or difference between the two sets of observations is the same or not, or 0. So in your parametric version of this, if you have parametric data, what you're conducting is a paired sample t-test, sometimes also called the dependent sample t-test. But if you have non-parametric data, then you'll be wanting to perform the Wilcoxon signed rank test. And there's probably other versions of this, but these are the sort of the most common, well-described, well-known tests for this sort of thing. All right, I added this slide on volcano plots because we do this a lot with our proteomics and metabolomics data. So most of you by now would be familiar with this kind of plot. All this is showing fold change versus p-value. And it doesn't even have to be necessary. And the reason why it's called fold change and why that's important is because it gives you a positive. If your data has gone increased in one group or decreased in another, this sort of shows you that left, right, up, down distribution. And then when you look at it, it's immediately obvious why it's called a volcano plot. It kind of looks like data spewing out of the top of a volcano. So your data is the lava, I guess. It's so usually with this, it's a combination of a t-test with a log ratio transformation. And it's a type of data visualization. So this isn't telling you about the distribution of your data, because now you're looking at the distribution of your p-values, your test results, versus a log transformed set of values. Like I said, it's usually used in genomics and proteomics and metabolomics. You should scale your data, but doesn't have to be normal. You can do a non-parametric t-test for this type of plot. So you could do the Mann-Whitney U or Wilcoxon paired test if you wanted to. All right, so if you're comparing more than 2 groups, then we move from the t-test into the multiple group test. And there's different ways to do this as well. So there is what's for the categorical data. You have your chi-square, which is sort of like an extension of the Fisher's exact 2x2 contingency table. And then for continuous parametric data, you have ANOVAs, MANOVAs, ANCOVAs, MANCOVAs. If you have non-parametric data, but it's continuous or discrete, and the chi-square test isn't appropriate, you can a Kruskal-Wallis test, which is like the non-parametric sort of equivalent to an ANOVA. And there are special cases for all of these where we have what's called repeated measures. This is an extension of the paired t-test. So if you're measuring the same subject over and over, that's a repeated measure. Also, sometimes you have one control group and many treatments, and you're comparing everything back to that same control group. So that's called a many-to-one comparison. So I'm going to go over all that right now. The chi-square test, also written as, I've got it as a big X squared, but it's actually the chi, supposed to be the chi symbol from your Greek symbols. And I think maybe that my chi there might have changed somehow, but you guys know the one, sort of like a squiggly X. The statistical hypothesis test, where the sampling distribution of the test statistic is a chi-square distribution when the null hypothesis is true. So if you have different degrees of freedom, by the way, your chi-square distribution is going to change, I think. And okay, the whole idea here is, can you tell the difference between these four groups? I mean, they're all chi-square distributions. Some of them are different. Again, it's sort of an extension of the Fisher's exact test, where you're kind of looking at observed and expected. But here you can have n values that are greater than 10. And as well, you can have, I think you can have multiple observations. So you don't just have to have A and B. You can have, I guess C and D are here. So you could have an E and an F as well. Although I'm saying that, but the chi-square is, I think it's called a squared test because it's a 2 by 2. So maybe I'm wrong. So the assumptions for this is random sampling, that your data is independent, mutually exclusive groups, and you use this when you want to test the difference between two variables and your variable of interest is proportional categorical, and you have two or more options. So you can do this with more options. This depends. You can only have two groups, but you may have more than one sort of measurement or option, and you have independent samples. And again, you can have more than 10 in every cell. Similar to this, you can look at analysis of variance, which is, or sort of similar to the t-test, I guess, but with just more than two groups. So now we're looking to see if the distribution means are significantly different. And where distributions overlap, sometimes there's no appreciable difference between the means and they could be the same. And this all has to depend with your, it depends on the variation in your data set. So that's why it's called the analysis of variance. All right. So conceptually, it's similar to a multiple two-sample t-test, but it's more conservative and it's supposed to result in fewer type 1 errors. So you may ask, why can't I just do a t-test of this and this, like red versus blue, blue versus green, green versus red? Because when you do that, you're going to start getting type 1 errors. And if you do it as an ANOVA, it accounts for the multiple comparisons. A two-way ANOVA is when you have two categorical independent variables on one continuous and independent variable. And then, so this is sort of a simple ANOVA, and a two-way is when you have, let's say you have male and female data for the exact same plot. Well, now you've got an extra category that you need to assess the differences within. Okay, the Kruskal-Wallis test is the non-parametric version of an ANOVA. So if you have three different groups and you aren't sure if the distributions of your data are different, or I guess here you're sort of looking at the mode, you want to know if the modes are different. And so this is for comparing more than one independent samples, and they can have equal or different sample sizes. Usually another assumption that I forgot to mention in ANOVA is that your sample sizes are similar. Or if not the same. But if you have dramatically different sample sizes, the Kruskal-Wallis test is more appropriate because you can do that. And it's an extension of the Mann-Whitney U-test. And then, of course, the repeated measures ANOVA is when you are measuring at different time points or levels, and the same test subjects are in each group. So the parametric version of this is called the repeated measures ANOVA. If you're conducting an ANOVA test in a packaged software, usually it asks you, do you want to conduct the repeated measures ANOVA or the regular one-way ANOVA or whatever? And so you just make sure that you understand what kind of data you have and check the box. If you're doing something a little bit more, it's your say, and you're doing something like R. I mean, I feel like if you're using R, you already have enough of an understanding of data and statistics to confidently pick the right test, but you may have to just find a different script. And then non-parametric is the version of this is called the Friedman's test. So that is the repeated measures version of the Kruskal-Wallis. All right. So post hoc testing is, okay, these tests that I just showed you can tell you if your data distributions are significantly different, but it may not be able to tell you which groups are different from each other. And there may be cases where not all the groups are different from each other. Maybe it's just one or two groups that are different from each other. So the post hoc testing allows you to identify which groups are different. So this allows you to do statistical analysis that were not specified before the data was seen. So that's why it's called post hoc testing. It's usually, like I said, to determine differences in groups. There are no, as I know it, no post hoc tests and non-parametric testing that are reliable. So that's one of the reasons why people like to do parametric testing and ANOVAs, because even though you can use a Kruskal-Wallis to identify differences, it's not always easy to tell which groups. I say this, but I'm pretty sure that GraphPad, which is another software we use a lot, does do some sort of post hoc test. So I feel like I might need to update this slide and go into GraphPad and find out which tests they're doing. And yeah, I'm just going to leave it at that. With the parametric test, there is a lot of post hoc testing available, and each one is a little bit different in its mathematical stringency or the way that it does the difference testing. We tend to use Tukey's HSD and the Dunnett's test a lot in our toxicological testing. But the Fisher's LSD is also really popular. We use that a lot in proteomics. I would steer clear from Bonferroni almost always. I think people find Bonferroni too strict. Maybe it's used in clinical settings more often when you really want to have a strict false discovery rate correction. But we wouldn't use it in environmental data sets very often because it's a little too strict. Okay, so I'm going to talk about Dunnett's test and why it's so cool. So a little bit of a sidebar. This is a post hoc test developed by a Canadian mathematician named Charles Dunnett. He passed away about 15 years ago. What this Charles Dunnett came up with is a way to do pairwise comparisons multiple times to a single control. And so if you're a toxicologist or maybe even a clinical, drug tester, this is really important. This is called the many-to-ones comparison. And before he came up with this test, no one was really doing it, but we actually often use this type of test in our research. And it's a special case of the multiple comparisons problem. So the multiple comparisons problem is when you start comparing multiple groups over and over, you can start to get a false discovery rate. Or false discoveries, the rate of false discoveries will increase just based on the statistical concept that the more tests you conduct, the more likely one of them is going to be incorrect, just due to chance alone. And so this is a version of correcting that is particular to when you're comparing everything back to the same control. It's hugely influential in toxicology. And so when I was learning about this to write this slide, I didn't know Dunnett was Canadian until I was preparing these sets of slides last year to start doing these talks with you guys. And I thought it was neat. So there you go. All right, let's talk a little bit about MANOVA. MANOVA is when you have one independent variable, but multiple dependent variables or responses. And so here's an example of a one-way ANOVA. So you've got test scores and level of education that you're looking at. A two-way ANOVA example is when you have the same categories, but the same tests, but on two different categories. And you want to know if, for instance, people with the astrological signs of Libra versus Pisces are going to have different test scores. I mean, it's absolute nonsense, and that's why we have these slides here. You might expect level of education to affect test scores. We probably wouldn't expect zodiac sign to do that. Anyway, this is what we're talking about here. This is the MANOVA. So the independent variable is degree of education, and the dependent variable is, for instance, test score or perhaps annual income, which we didn't have. So you can an ANOVA with several independent variables is sort of this, a two-way ANOVA is a MANOVA. So this is when you're doing extra crosses. I feel like I didn't explain that clearly. I just confused myself. But anyhow, you can do a one-way MANOVA or a two-way MANOVA. But this has to do with having independent variables and dependent response variables. So the assumptions for this are the same as for an ANOVA, that the data are normally distributed, there's homogeneity of variance, the data are independently sampled, factors are discrete, or the variables are discrete, and the dependent variables are continuous. So you've got these categorical variables as well as continuous variables. There's one extra assumption that's not the same as you would have for ANOVA, and that's when there's one controlled variable and one response variable, and there cannot be interaction between them. Interaction is when the effect of one independent variable appears to depend on the effect of the other independent variable, which suggests that they are not independent. And in fact, they may be dependent on each other or influenced by a nuisance variable that you have not yet identified. All right. Examples of interaction. So if the main effect of A is bigger for B than B2, and B, I'm just not really understanding what that says. So you're measuring these different A measurements and you're getting these means. And so if you want to know, okay, that's it. So you want to know if the effect for B1 is different than for B2. So you've got these two sets of responses, but you want to know if one is changing differently than the other. So this is your classic MANOVA example where you might do a test and find out that they're different. But in a MANOVA sort of interaction problem, you can't separate the effects. You can also have suppression where one is suppressed as one goes up. But the worst would be when you have full interaction where everything is, or not interact. Is this interaction? Yeah, where everything is just in a totally different direction, and it could be misleading and inaccurate, and everything appears to be zero because one variable goes down and the other one goes up. So it'll look like there's no difference, but there may actually be differences. Okay, now analysis of covariance. This is when you can kind of blend a linear model with an ANOVA. So it's like ANOVA and regression. Okay, see you later, Sarah. It evaluates whether the means of the dependent response variables are equal across different levels of the categorical independent variable or the factor of treatment. So you have a dependent response variable and two independent variables. So you have a factor and a covariate. Statistically, this controls for the effects of other continuous variables that may not be of primary interest, which are usually known as covariates or nuisance variables. So basically, to make this sound more logical and looking at this figure, you're trying to figure out if a variable that changes over, weight or time or whatever it is you're measuring, if the two groups are changing uniformly or not, or if they are different. I'm looking at it as like a linear regression. This makes it even clearer. Is there a difference between this line, and this line? Are the slopes different? Looks like in this example, no, they're not appreciably different. But how do you know? You can't just use it with your eyes. You actually need to do a test to find out, is the variation around these regressions so large that you could actually pool these together because they're the same, or are they different enough to suggest that maybe one group is different and the other two are the same? Okay, so you can compare two different regressions, and that's pretty cool. So I can't remember who this came up with, who it was I was talking to, but very recently there was a student, I think it might have been Charlene in JP's lab, where you can actually do this ANCOVA sort of test. So the assumptions here are that the linearity between the covariate and the outcome variable at each level of the grouping variable are linear. So you can check this by doing a group scatter plot of your covariate and outcome variable. And also your regression slopes need to be homogeneous. So the slopes of the regression lines by the covariate and outcome variable should be similar or the same for each group. So this assumes that there's no interaction. If your slopes are going in opposite directions, that's interaction. You can't do this test. So basically, you want to know if the regression lines are parallel, and if they are parallel, you're trying to figure out if there's a difference between those parallel lines. Are you getting maybe an inhibition or an increase, something like that? Your dependent variable should be approximately normally distribution. Remember, I told you that for both ANOVA and linear regression, the assumptions are that your data is normally distribution and it meets that assumption. And you can check this doing the Shapiro-Wilk test. And you should also not have heteroscedastic data. You should have a homogeneity of residuals and variance. And as well, there should be no significant outliers. So if you have a couple of outliers, you can do an outlier test, maybe using Hoteling's T with a PCA, remove them, then you can do this. And this might actually also apply to PLSDA, which is slightly different, but has its own sort of regression analysis built into it. So you're going to have a more accurate PLSDA, which is like a regression, if you remove your outliers first. Okay. So here's your summary of all of these tests, because it was probably really confusing. So we've got the MANCOVAs, the ANCOVAs, the MANOVAs, and the ANOVAs. So the ANOVA is the analysis of variance. It's a test for more than 3 groups, and you want to know if there's differences in the sample population mean. So in the examples I had been showing you, it's figuring out if different education levels is going to change your test score. In a two-way ANOVA, you're checking to see if two different variables are going to affect your response variable. In the MANOVA, you're checking to see if you have 2 or more continuous response variables from the same categorical kind of style data. So if you just have one category, education levels, that you're checking to see if test score or monthly income would change, then you're doing a MANOVA. And then if you're checking to see if there's any crossover change between your response variables and your discrete categorical variables, and you have 2 or more, then you're doing a two-way MANOVA. And then you can include the covariance idea, where you're looking to see if there's a continuous variable or covariate that changes when you compare these. And the MANCOVA is the sort of linear regression test version of the extremely complicated two-way MANOVA scenario. All right, so we're about to wrap up. This is a table I made for you to know which inferential statistic test is the one you should conduct. So the things you need to know is, are your data continuous and does it meet the assumption of normality? If it is, and you have 1 sample, 2 samples, or more than 2 samples, and you're trying to tell, for instance, is there a difference between your means, then you would do one of these tests. If you want to know if there's a difference between your standard deviation, then you would do one of these tests. I didn't talk about the Bartlett's test or the F test, by the way. Sorry about that, but I think this is a very rare case. People hardly ever do these tests. Continuous and non-normal data would be non-parametric. So then you're checking to see if your median, not your mode, I kept saying mode, if your median is going to be different. And so you're testing for 1 sample, the Wilcoxon, for 2, the Mann-Whitney, and for more than 2, the Kruskal-Wallis test is applied. And then if you have discrete data that is not continuous and proportion, for instance, then you might want to be doing proportion tests, which I think, again, if I go back, is either a chi-square or a Fisher's exact test. All right. This one is a more complicated version of what I just said, but it has way more tests in it. And it's sort of like a flow chart. So you pick what kind of test you want to do. Do you want to predict? Do you want to measure the association between 2 groups? Like if there's a relationship, do you want to compare 3 or more groups? Do you want to compare 2 groups? Do you want to compare 1 group to a hypothetical value? Or do you want to just describe the groups? And then you can go through these sort of like decision trees and find yourself at a particular test, which is in the light blue, that you can conduct. And so the key here is if you have ratio or interval data, ordinal data, normal data, nominal data, or non-normal data. So I tried to teach you about all of that so that you could go through this. And there's way more tests here than I went over because I couldn't possibly cover everything in one go. But I gave you enough information that you should be able to figure out, if you start with the repeated measures, but then end up at a Friedman test or a Cochrane Q test, that you'll understand what that is and be able to confidently pick it. Okay, are there any questions? We have a couple minutes, and if not, I have a list of some more resources that I find really useful here that you can always go to.